Okay, so let's look at the third method, known as the elimination method. Same thing though, I'm trying to solve a system of equations. In this case, I'm trying to find a number for x and y that works in both equations. Are you with me? Okay, so let's look at this third method. Step 1, make certain the equations are in ax plus by equals c form with no fractions. Okay, so let me back up. Make certain the equations are in ax plus by equals c form. What does that mean? It means make certain the x's and y's are on the same side in alphabetical order, because x comes before y, and all those numbers that don't have an x or a y with them go on the other side. Got it? So let's look at the first equation. X and y are both on the same side, and this does not have an x or a y, so it's on the other side, right? Same thing in the second equation. X and y are on the same side, and this guy without an x and a y is on the other side. So we're good there. And it says with no fractions. Now here's the deal. Fractions aren't bad to deal with, but let's work smart and not hard. It's actually quicker and visually easier to work with these equations when there are no fractions. So look at equation number 1. I want to get rid of those 3 denominators, don't I? So here's the deal. I need a common denominator, agreed? So what's a common denominator between a 2 and a 4? Yeah, 4. That's the common denominator. So here's the deal. I am going to multiply both sides by 4. Well, on the left side, I've got 2 terms. So both terms need to get multiplied by 4. And sometimes it's easier to write it this way on the left so you can literally see the 4 next to each fraction. Does that make sense? Okay. So do you notice these 4's will cancel, which will leave me, good, that'll leave me 3x. Do you notice this 2 and this 4 cancel, which puts a 2 there, right? Because 2 goes into 4 twice, which leaves me minus, what's 2 times 1? 2, leaves me 2y, equaling, looks like these guys will cancel, right? And that goes in there twice, negative 2. Cool? Okay. Second equation. Yay, there are no fractions in front of the x and y. However, there's a fraction on this side, and I really don't want to deal with a fraction on either side. So, what are you going to do? Yeah, let's multiply everything by 2, because when we do that, those cancel, don't they? Which will leave me 2x plus 2y equaling negative 3. Awesome. We good so far? Okay. Now, the second step says choose a variable to eliminate. Now here's the deal. Eliminate means to wipe out, doesn't it? So you have a choice. You can wipe out the x's or you can get rid of the y's. Your choice, it doesn't matter. You're going to get the same answer either way. Any takers? Some of you are saying x, some of you are saying y, some of you are like, I don't know, I don't care. Okay, so you know what? I think most of you said x. So we're going to get rid of the x's. Cool? All right, hang in there. I'll be right back. Okay, so we just decided to get rid of the x's, didn't we? So let's look at the third step. If necessary, does that mean it's always necessary? Nope. If necessary, multiply to get the coefficients. Remember what the word coefficient means? Yeah, the number in front of the variable. If necessary, multiply to get the coefficients of the variable you are eliminating the same and opposite signs. So we opted to eliminate the x's, which means I need the numbers in front of the x's to be exactly the same and opposite signs. So take a better look at this. Is x, now that we know step 3, is x the better variable to get rid of? Or might y be the better variable to get rid of? Yeah, I'd say the y's. Why? Because aren't the numbers in front of y exactly the same number? They're both 2's. And they're opposite signs, aren't they? So maybe we should change our minds. Maybe we shouldn't get rid of the x's here. Maybe we should actually get rid of the y's. Does that make sense? Yeah, it does. Here's why that makes sense. Because after we do step 3, which in this case it was done for us, step 4 says add. You're like, what do you mean add? Literally what it said, add. I want to add these two equations together. And I can only add things that are the same, which means x's get added with x's, y's with y's, constants with constants. So, if I add the 3x and the 2x, 5x. If I add the negative 2y and the positive 2y, they eliminate. They wipe out. Wasn't that our goal? And equals, if I take negative 2 and add it to negative 3, good, negative 5. So when we add, we actually eliminated the variable that we wanted to, which in this case was y, after we changed our minds. Make sense? Okay, instinct tells you to do what here? Yeah, I heard you, divide by 5. So step 4 isn't just add. Step 4 is add and solve. So in this particular case, dividing both sides by 5 gives you x equals, yeah, negative 1. Does that make sense? Cool. Done? Yeah, no. How come? Because don't we still have to solve for y? Yeah, step 5 is solve for y. Or solve for the other variable, I should say. With me? Step 5 is solve for the other variable. Okay, now, I'm going to rewrite the original two equations. So we had 3/4 x minus 1/2 y equal negative 1/2. And the other equation was x plus y equal negative 3/2. Those were the original two equations. Agreed? Okay, so we're going to take this and always plug it back to the original equation. Because if I plug it into one of these and I made a mistake here, then my other answer is going to be a mistake also. So I always want to go back to the original equation. So which one do you want to plug it into, the first or the second? Yeah, I'm with you. I'm going to go plug it into the second one. So x is negative 1, right? So we have negative 1 plus y equals negative 3/2. What do you got to do? Add the 1 to both sides. So negative 3/2 plus 1. And yes, I'm hoping you remember how to add fractions without a calculator. Y equals negative 1/2. So it looks like we have the point negative 1 comma negative 1/2. Right? What does this mean? Yeah, some of you said it. That means if you literally graph these two equations, they would intersect, right? They would have an intersection, right? And they would intersect at this point, wouldn't they? Okay, so what kind of system is it? Good, it's consistent. It's a consistent system. Why? Because it has a point of intersection. Cool? Okay, there's one more step. We've talked about 5 steps. There's one more step. Any idea what step 6 is? Some of you do. Check! So take this solution, take this point, this ordered pair, plug it into both equations, and make sure that it works. I'm going to let you do that one on your own. In the meantime, I'm going to go get us a second problem. Okay, still solving using elimination. Let's look at problem number 2. Did you get the steps written down? All right, pause the video, go back, write the steps. I'll wait. Okay, you're back. Let's go. So first step of the elimination method is make certain that the equations are in ax plus by equals c form, correct? And no fractions. Well, gratefully on problem number 2, there are no fractions. Okay, so first equation, yeah, 3x plus y equals 1. Check, that one's good. But equation 2 is not in the right format because the x's and y's are not on the same side, are they? Okay, so we said equation 1 was good. So that's 3x plus y equals 1. But equation 2, it looks like I have to move the 6x over, don't I? Add the 6x to the other side. So I'll get 6x plus 2y equals 2. Good. What's my second? Yeah, eliminate a variable. So what do you want to eliminate, x's or y's? Yeah, in this case it doesn't really matter, does it? Because the coefficients are not the same on either variable. So I'm going to have to multiply either way. So what do you want to get rid of? X? Okay, let's get rid of x. So we're getting rid of the x's, which means we need their coefficients to be the exact same number and opposite signs. So, well, this is a 6, this is a 3. Can't I turn a 3 into a 6? By doing what? Multiplying by 2, correct. Are you going to just multiply the 3x by 2? Good, you're not. You have to multiply the entire equation, don't you? Because math is balanced. If you do it to 1, you got to do it to the whole thing, don't you? So I'm going to multiply this top equation by 2. And that'll make the x in the first equation a 6x. But one of them's got to be negative because it said same coefficients but opposite signs. So, yeah, multiply that first one by a -2 and we'll be good to go, right? All right, so let's keep looking at this. That means I'm going to get a -6x minus 2y equals -2 for the first equation. The second equation, not doing anything to it, right? And then, now that the x's have the same coefficient of opposite signs, what do? We get to add. So let's add these guys. And they drop out at, oops, bonus, x's and y's dropped out. So I end up with 0 on this left side, don't I? Well, so be it. If they're going to go, let them go. 0 equals, 0. Okay, what's the deal here? 0 equals 0. The variables dropped out. We've seen this before. It was in the substitution method, but I don't care because it means the same thing. If all your variables dropped out and you are left with a true statement because 0 does equal 0, then these lines, when you graph them, are the same line. Which means this is what kind of system? Yes, this is a dependent system with an infinite number of solutions, right? Okay. So remember, though, how we can write the solution. The set of the point xy such that, yeah, the 3x plus y equals 1 is the reduced form, right? It has the smaller numbers. So 3x plus y equals 1. And then close off the set. Good? Awesome. All of these methods, they all have their purpose. But regardless, what happens here at the end connects from one method to the other. All three methods tell me the exact same thing. Got it? They all tell me the same thing. If they're the same line, that means I end up with a true statement for substitution and elimination, which means they're dependent with an infinite number of solutions. Just like the last problem, I actually had a point of intersection, which shows it on a graph, which shows it on substitution. I end up with a point of intersection. Good? Okay, let's look at problem 3. So, are these two in the right form? Yay, they are. Now, pick a variable to eliminate. What do you want to eliminate, x's or y's? And let's go for the y's this time. We solved for x on the other one. Well, we got rid of the x's on the other one. Let's get rid of the y's here. Okay, so they have to be the same coefficient and opposite signs. So 7 and 21. Yeah, make the 7 into a 21. How? Multiply by 3. Well, that'll make it a negative 21. And this is already a negative 21. Good, which means I have to multiply it by a negative 3 to make it a positive 21. Cool? Okay, so what's the first equation look like? Negative 12x plus 21y equals negative 21. Second equation is still 12x minus 21y equals 24. Then what do we get to do? Yes, we get to add. Oh, x's and y's dropped out. I end up with 0 on the left, don't I? Okay, equals 3. Uh-oh. Does 0 equal 3? Nope, this is false. What does that tell you about these two equations? Yeah, these two equations would be parallel lines if you graph them, wouldn't they? Because a false statement meaning parallel lines means no solution, which means it's an inconsistent system. Got it? Yeah, admit it. You knew that that problem was going to work out that way, didn't you? Of course. I had to show you what it looked like in the elimination method. Of course. Anyway, you have 3 methods of solving systems of equations. Graphing is good because it gives you a visual representation of what's happening, but really the better 2 methods are substitution and elimination. And I'm going to tell you right now, if I have something like problem number 3, more than likely, a good 99% of the time, I'm going to use elimination on this one because there's no way I want to solve for x or y because I'll end up with a bunch of fractions and I don't want to deal with fractions. Make sense? Okay, you have fun with these methods and I'll catch you on the flip side.